Hello, this is our GPU project. I'm Josh. We also have Matthew and Connor who worked on
Hello.
this,
Oh,
Hey,
and we're going to tell you about our project. So imagine that you need to do a ton of calculations really fast. A regular CPU or processor that you might have seen in CPE 233 or in your laptop or computer does things kind of one at a time usually. And so there are certain situations where you would need to do things much faster. So imagine if you had something like this, an array, like a 2D array or 3D array, and you wanted to do like y equals ax plus b on every single thing in this array. If you have a regular CPU, it's going to take you a long time. Now, imagine if you had a ton of these things. You're going to be sitting here for hours. But now imagine if you could if you could process y equals ax plus b on multiple different blocks at the same time in parallel. This would allow you to really speed things up and get this job done a lot faster. And that's kind of the idea behind what a GPU is. So it's utilizing a lot of different cores to do thousands of calculations all in parallel at the same time. And this is really useful for image processing where you're trying to do calculations on all the different pixels on your screen.
all right. So when we first started on this project, we were interested in GPUs, and we started digging deeper, and we found that the heart of the GPU is the stream processing unit, which is, you can kind of see here on the right, this is NVIDIA's GPU layout. So we started to target that, and we made a goal for ourselves that we wanted to recreate this layout here as close as we can and get it working. So kind of the major targets that we wanted to hit was to do multiple computations in parallel for multiple units. You can see here there's like 8 or so stream processors in the middle that are dark blue. So we wanted to make our own stream processors that could all run in parallel just like they are here. So yeah, Hugh, next slide. And then, so this is our actual working layout here. So we have 3 main blocks. On the top is the instruction register in green, and its job is to hold the instructions and administer the instructions to each of the stream processing units at the time the stream processing unit is calling for it. And it kind of makes a queue, and we'll pass that out in a uniformly distributed way, like evenly over time. And note here, there's only one stream processing unit. This is expandable to as many units as you want, to sort of certain limit. We have some limit we haven't really found yet. And then on the bottom right corner, we have the memory cache, and that's the data set that all the stream processors are working together to do their computations on. So this is kind of like that big block that Josh was showing you earlier that needs to get worked on. And finally, in the bottom left, we have the stream processing unit, and this is kind of the heart of it all. It is essentially like the ALU you built in 233 with a little bit different commands, and that's pretty much it in the most basic sense I can make it. So the cool and interesting things we kind of got out of this was getting the timing of everything to work together. So we ended up simulating this with 4 stream processing units, and they were all running together and doing their calculations, working on the memory cache, which is kind of cool to see. And that kind of exhibited the strength of parallelism. So if you imagine again back to that block that Joshua was showing us earlier, so if we only had one processor chomping away at that huge block, it would take a lot more time than it would if there was 4 of those chomping away at that block. And modern GPUs today have hundreds of these processors linked up. So you can imagine like one processor versus 100. It doesn't matter how smart the one processor is, it still has to do all the work, but 100 of dumber processors can get it done quicker. So that's what kind of the whole gist of this is. The expandability kind of plays with that idea too. So like you can just keep adding stream processing units to make the whole process go quicker. Yeah.
And then now moving on to something unique. So something unique about like that makes us different than the like almost like the 233 ALU, kind of like these SP units also do floating point math. So floating point math is different is that it's 32 bits. There's 1 bit designated for the sign. There's 8 bits designated for the exponent, and 32 bits, oh no, 23 bits designated for the fraction or the mantissa. So how it works is there's the 1 for the sign, so it's 1 or 0 depending if it's positive or negative, and there's 8 exponent bits that allow for 127 2 to the 127th power or 2 to the negative 127th power, depending on that first bit. As you can see, it takes the whatever the value is and subtracts 127 by it, and that's how it gets it and how it allows for the max value. And then the mantissa bit also is an extended fraction bit. So as you can see, it's almost like as if you placed a decimal and started adding binary after that. So you can see we have, for example, on the picture, it says 1/2, 1/4, 1/8. And what's cool about this is that it allows for really, really tiny small values and really large values. So you can see the max is 2 to the 127th and the min is 2 to the minus 127th for like positive values, which ends up being like 10 to the 38th and 10 to the negative 39th, which are extremely large and extremely small. The cool part about this is that it allows these values to be stored in only 32 bits, so it allows much larger numbers in smaller amounts of bits, and it's signed, so it's really easy to translate in between signs when needing to use them. So moving on to the math that is done with floating point, we can begin with add and subtract. So they're a little complicated of how they work with floating point math, is it because there's an exponent and a sign and and this mantissa fraction bit. So how it ends up working for add and subtract is that it takes the exponent bit and it shifts and like normalizes or shifts the mantissa bits to a point where they line up. So by basically comparing those exponent bits and finding which one's larger and the difference between that, and does a shift operation. From there, it'll add those mantissa and take those equalized exponents and then create and round to create this overall new value for addition. So the cool part about this is that it's very straightforward. There's a few exceptions to it, but you're able to still, again, add large and small and subtract large and small values. Subtract is literally the same as the add, except literally the sign bit is just flipped on the second number. And then lastly, we move on to the multiplication and division. So these are really cool as they look a lot simpler and they're a lot easier than the addition and subtraction portion. So you don't have to like do all the shifting. In this case, you do multiplication, which again, multiplication in hardware is a lot more intensive, although it looks much simpler. So in this case, for multiplication, it's multiplying the two fraction mantissa bits and adding the two exponent bits together. And then same with division is dividing and then subtracting the exponent bits. These are both very straightforward, but the problem is that they're very easily subject to overflow and divided by 0. So, and especially with multiplication with the overflow, as you can saw the values get very large, like 10 to the 38th. Like if you start getting values larger, like larger and larger, and you start doing multiplication with those values, they start become larger and larger, and then even with the smaller ones, it becomes too small that to the point where it just becomes 0. So there are some limitations, but the thing is, they're still really good as even like multiplication, you can still store up to 10 to the 38th power, which is insane. And it was really cool exploring this for this overall project, and I was something I didn't even know existed until, I guess, this project. So yeah, and then we'd like to thank you guys all for watching our amazing video.